So in the last class, I was telling what? That basically this is one of the asynchronous counter. Okay. Hopefully, I am very much hopeful that you might have revised everything. So you can see over here that all the flip-flops have basically what? They have del t propagation delay, and you can assume this that basically, just give me a second. Yes. So you can assume this that all the flip-flop are basically what? They are identical in nature. So that is why they have the same propagation delay. So now I asked you whether this is up counter or down counter. So you can see this is the external clock pulse. Okay. So this is negative edge, and the subsequent flip-flop, it is taking the output from your non-complemented output. So non-complemented output corresponds to plus. So you can see over here that this is what? This is your up counter. Okay, this is up counter because it is counting up. So if this is up counter, so you can see what the counting sequence will be 0 0 0, then 0 0 1, like this till 1 1 1, and again it will become 0 0 0. Okay. So basically we know everything up to this point, that how this count is going on. But actually, how is the machine decoding the count states? Like, how will the machine know whether if this is 0 state or 1, 2, 3, 4, like till 7? How does the machine knows basically, or how do we basically decode the states? Okay, even we need to know that your flip flop, it is at which state. Even we need to know this. So how are we going to know that? So with means we have what? We have your decoding circuit. So very quickly, I want all of you to draw, means later on you can draw the diagram. At the moment, you just see over here. Okay. So you can see the moment this is 0. So I have told you what? That all of the propagate means flip-flop have propagation delay of del t. So this is the external clock, this clock, and I am giving the clock pulse to this A flip-flop. No need to copy down at the moment. You guys just see the lecture. I have told others also that today we have session. Why others haven't joined yet? So even Piyush told me. Just let me check. Yeah. So I was telling what? That basically we need to decode the states. Okay. So how do we actually then decode? Look very carefully. So the external clock has been supplied to this A flip-flop. And this A flip-flop, it suffers from propagation delay, that is del t, and this is your negative edge triggered. So let us assume initially all the flip-flop are reset. That means QA, QB, QC are 0 0 0. So that means if initially this is 0, see if this was ideal flip-flop, that means 0 propagation delay, then at the clock instant, whenever we have negative edge, transitions would have taken place. Okay, transition would have taken place. But this over here, we have del t propagation delay. So this will not be like this. So over here, it will be something like this. So I will take a considerable amount of delay. You can see over here that this is a very considerable amount. But usually such means such a large amount of delay, it doesn't happen. But here I am taking. So first understand, then you can write. Okay. First understand. This is very important because few of the questions have been asked recently in your GATE paper. So basically, this time it is what? It is del t. Okay. So I will be erasing this. Just for explanation purpose, these all time, these are basically del t. You can see whenever there is a clock edge, after del t time, there is a transition in state for the flip flop A. Okay, so I will be erasing this. So let me write it as QA, or very simply I can write it over here that this is what? This is your del t. Now look, basically the negative edges of this A flip flop QA is acting as your clock pulse for this B. So now if you see, negative edges we have are over here, 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 here. Okay. So at all the places we will have what? We will have your transition for QB. So I have assumed that initially QB is also 0. So look very carefully. I should have drawn one more. Just give me a second. Please understand the concept very carefully, because I am telling you there are a lot of questions you will find from this concept. So now ideally your transition should have taken place over here, but as there is del t propagation delay over here, so this flip flop will also transition after del t time. Okay, you can see. Now you can see basically this time, if I zoom a little bit, so this much is actually what? This much is del t. But if you consider from here till here, this is what? This is 2 del t. Del t for here and one more del t over here. So this is 2 del t. Now basically this QB, it acts as your, basically this QB, so this is your QB, this is acting as your clock edge for this C flip flop. So all the negative edges, it is going to be what? It will act as your trigger. So you can see there is one negative edge over here and one more over here. So let me take, I have to mark once again. Let us use this color now. So let me use now black color. Okay. So QC will look something like this. So you can see this is the negative edge. If this was ideal flip flop, your transition should have taken place here only. But you can see there is a propagation delay del t. So what will happen? After del t time, transition will take place. Okay. So now look, this is what? This is your QC. And see very carefully. This much time is del t. This is also del t, and over here this is also del t. That means from here to here it is what? It is 3 del t. So the maximum propagation delay that we can see, it is what? It is 3 del t. Tell me, up to this point, is everything clear? Is everything clear? Tell me yes or no. Is this clear? Everything? Any doubt? So very quickly I want you to draw this diagram up to this point. So very quickly draw. Very quickly. So I'm giving you 1 minute. Quickly draw this diagram and let me know. So you can, okay. So first draw this much. Have you completed this one? Okay. Or else later on you can draw. Just see first what is happening. Then later on I will give you 2-3 minutes. You can copy down the entire thing. Now look over here. So I have used up all the colors. So let me see if I can get some more color over here. This brown color is fine. So you can see, let us write the counting states. Okay. So this is your 0th clock pulse. This is first clock pulse, second, third, fourth, fifth, sixth, seventh, and this is 8th clock pulse. This brown color is not making that much difference. I don't know whatever this color is. Okay. So over here you can see this is 0. This small place for del t also it is 0. Okay. Here it is 1. For the small place it is also 1. Here it is 0. Here 0. Here 1. Again here 1. 0, 0, 1, 1, 0, 0, 1, 1. Again 0, 0. This will continue. Now look over here. Here also it is 0. So I will extend this till this point. You can see this point is also 0. Please pay attention over here because the diagram is going to get very clumsy. Okay, so please pay attention. You can see at this point it is what? This is 0. Here you have 0 at the small instant at this del t, and over here you have 0. Okay. So this is 1, 1. Over here also you have 1, 1, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, and this is 0. Fine. Now look over here. This is 0. This is 0. Okay. Over here you have 0. You can see this is also 0. 0. Here also you have 0. 0. Over here also you have 0. 0 and 0. Okay. Now you have 1, 1, 1, 1, 1, 1, 1, 1, 1, and here again you have 0. Now look very carefully. Very carefully you see, if this del t, first case, up till now we have assumed that this del t is very, very smaller compared to the time period of clock. Okay. So we have always neglected this. But now what is happening, that this del t is comparable with this clock pulse. It is comparable. Last time it was very, very smaller than TCLK. This time it is smaller, but it is not negligible compared to TCLK. Now look how will your counting states take place. So you can see basically over here this is 0, 0, 0. So this will be 0. But you can see even this place over here, this is also coming out to be, so I should use some different color. Let me use red color over here. So this is 0. This is also 0. Now look over here, what is the count? You get 1. So this is basically what? This represents the delay. This is the delay in the counting state. So this is your original 0. After this, you can see for the small amount of time del t, after this first clock edge, okay, you can see this is still 0. So this basically represent. So let me use some different color. So whenever I mark this red color number with a blue circle, that means it basically represent a number with blue circle. It represents the delay in count state. In the normal counting state, it is representing a delay. Now look over here. This is the normal number 1. After that, you can see what you are getting. You are again getting 1 at for the small instant. So this is also the delay in the count state. So I will encircle it with a blue color sign. So it means blue color pen. Now look momentarily over here. What do you get? So this is also 0. You can see over at this point 0, 0, 0. So over here you get 0, and this time I am encircling it with a black color. So whenever I encircle a number with a black color, this is known as your glitch or unexpected count. Now why this is unexpected? Because after 1 I should get 2, but here I am getting 0. Why? Because due to this propagation delay. Now look, after this what I get? So this is 0, 1, 0. So that is 2. This is your normal count. Now look at this point. So I should have used the same color, because if I use some different same color, this will be problematic then. So look at this point. So here you can see this is 1, this is 0. So what I am getting? I am getting 2 once again, but this 2 is actually what? This is the delay. So this is normal. Now look, after this 2, what am I getting? I am getting 3. So this is your normal number 3. But now look very carefully over here what we get. So let me zoom in a little bit over here. So look over here very carefully. So for this particular small time, okay, for del t time, means from here to here, okay, from here to here, what is the count? You can see basically this is 0, 1, 1. So that means I am getting 3 over here, and this 3 is actually the delay. So I am encircling it with blue color pen. But after this, look, for this instant, this one, and over here, whatever we get for this much time, so that is 0. So that is what? 0, 1, 0. So that is 2. So this is a glitch. Once again, we are getting. So for glitch, what was the color code I had given? Okay, so black color. So this is a glitch, unexpected count. Now, once again, if you see for this much time, okay, this and this, it is 0, over here 0, again 0. So you are getting 0 over here, and this is also an unexpected count. This is also a glitch. So I will mark it over here like this. Now, similarly, you can do for the rest of the time also, but I am doing it up to this point, or else let me fill it. Okay, it's okay. So let me write. Next is 1, 0, 0. So this is 4. So this is the normal count. You can see over here for this much small time. So this is 1, 0, 0. So this is also 4. But basically this represents what? This represents your delay in state. So next we have over here is what? 5. Okay, 5. And this is also 5. You can see over here. So this represents what? This represents your delay. So delay will be represented with blue color. Next, you can see once again over here, you will be having some kind of glitch. And what will be that? You can see this is 0, 0, and this is 1. So you are getting 4. So 4 is an unexpected state over here. So this is glitch. Okay, this is glitch. This 5 is basically the delay of this. Okay, so I have encoded it with blue color. Now look, what is the next state? So this is 6 over here. Once again, you are going to have what? You are going to have 6 as your delayed state. So this I am going to color code it with black color. Sorry, blue color, because it is your normal count. Similarly, over here, you will have 7 and again 7, but here it will be delay. So delay will be represented like this. And in the next clock, you can see this is 110. So you are getting 6. So 6 is an unexpected count after 7. So this is a glitch. And after that, once again, you can see this is 100. So that is 4. 4 is also unexpected. So this is your unexpected count. So I am going to encircle it with black color. And after that, once again, you are seeing what? You are getting 0. Okay. So this is your counting states. Okay. These are your counting states. So let me remove it. You can see all the places where I have written without encircling. Those are your normal count states. 2, 3, 4, 5, 6, 7, and then 0. But in between, momentarily, I am getting sometimes delay and sometimes glitches, like over here 2, 0, over here 6, 4, over here I am getting 4. So these are all unexpected counts that I am getting. So tell me, up to this point, is it clear? So make this diagram in your that landscape mode, okay, in your notebook. So very quickly, I want you to make this diagram. So everything, have you understood? Tell me, is this clear? Anyone have any doubt? Let me know. Chandana, Piyush, Raju, any doubt? So quickly draw the diagram and then I am going to tell you a few more things. So is this visible properly to you guys? See, if you draw it properly, you will get the glitches on your own. Okay. So draw this quickly. Is it done? Tell me yes or no. Okay, quick, be quick. So you can even draw this diagram. Okay, so this is very simple. You can see this line is what? This is QC. This is QC complement. This is QB. This is QB complement. This is QA. This is QA complement. So when you want to decode 0, basically all the lines of this AND gate has been connected to QC complement, QB complement, QA complement. So what will happen? All the lines will be active high, and over here we have basically this is the symbol of LED. So whenever QA, QB, QC, all of them are 0, 0, 0. So this line QC complement, QB complement, QA complement, it will be high. So this will be 1 and this is LED. So this will glow. When your QC, QB, QA are 0, 0, 1. So you can see this line will be high, this line will be high, and this line will be high. So this will be 1 over here and this will glow. So like this will continue to glow. So you can see I have drawn it up to this point. So very simple. Okay, very simple I have drawn. Now this diagram is actually incomplete. I will tell you why. Okay. So first, very quickly, you draw this diagram. First you draw this. Okay. First you draw this and then you have to draw that diagram. So draw this very quickly. I am going to wait. It's okay. So I'm going to wait 2 minutes, okay? Is it done? Completed? Okay. So now draw this diagram very quickly. And take your time. I will give you 2-3 minutes to write everything in your own language, whatever you have understood. Completed? Is it done? Chandana, Piyush, Raju. Completed or not? Means I am sitting. Okay, so be quick if you haven't completed. Done, everyone? Done, fine. So now tell me one thing, the glitches you can see, in which part of the clock is the glitches taking place? Glitch. In which part of the clock is it taking place? In the positive level or in the negative level? Glitch. where is it taking place? In the negative level of the clock or the positive level? So first mark where the glitches are taking place. So you can see one of the glitch, it is taking place over here. More two glitches are taking place over here, and these two are also glitches that are taking place over here. So you can see the glitches are always taking place in the negative level of the clock. You can see this, if you draw the straight line, so this part is happening in the negative level. Over here, if you see, I am drawing straight line, so this is also in the negative level. This is also, don't draw this, it will make your diagram very messy, so don't do this. So you can see, just for explaining, I am doing this. So you can see the glitches are always occurring at the negative level of the clock. So for avoiding the glitch, what I can do, I will be applying one more input to this AND gate, and that will be basically known as your strobe input. And how am I going to apply that? So basically in the negative level, so as glitch is happening in the negative level, if I stop taking the readings in the negative level, then the problem will be solved, because my counting, I need this 0, this 1, this 2, this 3, this 4, this 5, this 6, this 7, and once again this zeros. All this place means all these values are taking place in the positive level of the clock. You can see all of this is taking place in the positive level. This one, it is completely present in the positive level. This 0 is always present in this positive level. This 2 is present in the positive. 3 is present in this positive. This 4 is present in this positive level. So if somehow I take only the reading at the positive level of the clock, I won't be getting any glitch. So what we do, basically we have one strobe input, and that strobe input is connected to this clock. Now it will be very difficult for me to draw. Okay, fine. So let me do one thing. So basically this red color is your, what, this is your strobe input. Okay, and I will be giving each line the strobe. So what will happen? Basically in the negative level, the strobe input of all the AND gate, it is 0, because at the negative level, this is the negative level of the clock. So here only I have told you that glitch is happening and we don't want glitch. So this is 0, this is 1. So whenever one of the input of the AND gate is 0, output will be always 0. So none of the flip means none of the LED is going to glow in your negative level, and this is known as your strobe input. Tell me if this concept is clear or not. The concept of strobe input. Tell me, is this clear? Is this clear? Fine. So now one more thing. See, usually in GATE exam, in the last 20 years, never have they talked about strobe input. Okay. But if they ask sometime, so you should be knowing basically what is strobe input. Okay, fine. So up to this point, I hope everything is clear. Now, let me talk about few things. What is the maximum propagation delay that we saw over here? What is the maximum propagation delay? Look over here. What was the maximum propagation delay that we saw? We saw it at this point, that was 3 del t, and once again at this point, or at this flip-flop, basically I had the maximum propagation delay, and that was what? It was 3 del t. If I want to generalize it for a n bit flip-flop or n flip-flop counters, it will be what? It will be equal to n del t. So the maximum propagation delay is what? It is equal to n del t. Tell me, is this clear? 3 del t. Yes, very good, Chandana. For n bit flip flop, it will be n del t. Now, for the strobe input to be effective, see, glitches are happening in the negative level. So understand very clearly over here, later on you can copy. So this is TCLK, time period of 1 clock. And in this negative level, this is what? This is your TCLK by 2. Now, if suppose what happens, this means you can see this is being contained. So my diagram, it is going very, very messy over here. So you can see this is the point where your maximum delay is happening. Okay. And it is being contained in this TCLK by 2. But if suppose this delay what was coming outside this TCLK by 2, then I couldn't make use of the strobe input. Why? Because strobe input is taking place, means it is doing what? It is basically taking this negative level of the clock and eradicating or removing the glitches. But if suppose this was coming something like this up to this point, okay, means if suppose this waveform was transitioning at the positive level, so now you can see that even this strobe input is not effective. Why? Because we came out of this negative level, and in the positive level also we are having glitches. So that is why for the strobe input to be effective, so right over here, what happened? Computer is now, what is happening? Give me a minute. Just give me a second. It's even sometimes I feel 8 GB of RAM is very less. These days we have like, so I was seeing some very good laptop. So there was like 16 GB RAM. Okay. So means even 8 GB RAM, I feel it's very less. I am using 8 GB, but still sometimes my computer it's stuck when I do this video editing and all these things. Okay. So I was telling what? If this comes out even in the positive level, so then I cannot take help of the strobe input. So for the strobe input to be effective, so condition for strobe input to be effective, the propagation delay, the total propagation delay, that is what? N del t, it should be less than equal to TCLK by 2. So that means the maximum propagation delay, it can be in this negative level. If you go even outside this negative level, then what will happen? Your strobe input, it cannot help you in decoding. So tell me if this is clear or not, whatever I have written. Is this condition clear? Is this condition clear? Tell me yes or no. Is this clear? See, I said what? Basically, our strobe input, we had done what? Because all the glitches, it was happening in the negative level. We have seen I have shown you that this was one of the glitch. It was happening in the negative level. Here we have two glitch. It was also happening in the negative level. So now glitches are happening due to the propagation delay. Okay. And if suppose this propagation delay is larger than this negative level, what will happen? This will come outside like this. Okay. If suppose the propagation delay is larger than this TCLK by 2, then this will come out like this. In the positive level, you can see this part is what? This is the positive level. So over here, you will be starting to have glitches. So even your strobe input cannot help you. So for the strobe input to effectively kill the glitches, what should be the condition? That the maximum propagation delay, it should be less than the time period of the negative level, and that is what? TCLK by 2. So Chandana, did you understand now? Did you understand what I am trying to say? Fine. So quickly note this. Note this. So you can see now I can write, or I can even get the maximum clock frequency. How? So look over here. So this I can write 2 n del t less than 1 by f CLK. Okay. So I can even write it like f CLK max. Okay, this is the maximum clock frequency for propagation del t. It should be equal to what? It should be equal to 1 by 2n del t. So this should be the maximum clock frequency for what? For your propagation delay del t when there are n number of flip-flop. Tell me if this is clear or not. Or you can even write it like this. F clock should be less than 1 by 2 n del t. Okay. So this is the, wait, I have written maximum. Why is this maximum? So this should be the minimum clock frequency that we should have. Okay. This, sorry, that's what I am doing. So this should be the maximum clock frequency. I am correct. So this should be the maximum clock frequency is equal to what? It should be equal to 1 by 2n del t, or else clock frequency should be less than this value. It should be always less than this value to your, for your strobe input to be effective. Tell me if this is clear or not. Is this clear? So now one point to note. We never use this equation until and unless it is specifically mentioned in the question about strobe input. Okay. If strobe input is written, then only we are going to use this condition. Remember, if there is strobe input, then only we are going to use this condition. Okay. Then only we are going to use this condition. If strobe input is not there, if suppose there is no strobe input, so that means what? For condition, so now look, if there is no strobe input, so listen very carefully. If there is no strobe input, then we don't have this restriction that we only need to count in the positive level. Then in one clock means in one clock cycle, I need to count the states. So if suppose if we have this del t, if this 3 del t exceeds the TCLK, what will happen? I am telling what? If this 3 del t exceeds TCLK, then basically this transition which was taking place over here, now it will take place something like this, because your 3 del t is greater than TCLK. So what will happen? The transition, look here. Here your first transition should have happened. But as 3 del t is greater than TCLK and this much is what? This much distance is your 3 del t. So you can see what? The fourth number clock pulse count has been missed. So that is why for proper counting, when there is no mentioning of strobe input, it should be what? Maximum propagation delay should be less than equal to TCLK. So this is the condition for proper decoding when there is no mention of your strobe input, and this has been used numerous times in your examination. So now if you want to calculate the maximum clock frequency, so this will be 1 by f CLK, it will be greater than equal to n del t, or f CLK, it should be less than equal to 1 by n del t. So the maximum clock frequency, it is equal to what? It is equal to 1 n del t. So this expression has been used like 10-12 times in your gate examination. Direct questions have been given that for a synchronous counter, asynchronous counter, when each of the flip-flop has propagation delay given as 2 picoseconds, and when it is a 3-bit, calculate the maximum clock frequency that can be given when you want to decode it. Questions like that are present like in every alternate years, or every year they give such kind of questions. So have you understood condition? Tell me. So this is the most conceptual part that we have. Tell me, Chandana, Raju, Bhumika, you are late. So Piyush, Raju, did we understand? Bhumika, what happened? Today you are late. Piyush, what is this TY? Are you telling me thank you, sir? Mistype. You had some work. So now you won't be understanding what I am telling. So did we understand all the concept? Fine. So this was very important, that this is basically the maximum clock frequency that we can apply so that the asynchronous decoding can take place properly. Okay? Fine. So now over here, this is one of the counter. Okay? Can you tell me what kind of counting is basically taking place by looking in the circuit? Just look, copy this diagram and then let me know basically what is happening over here. Tell me whether this is asynchronous or synchronous counter. What is this? Asynchronous or synchronous counter? Asynchronous. Asynchronous. Okay. So why this is asynchronous means if this is your external clock, okay, so this two flip-flop are getting the same clock. So this is synchronous. And over here you can see basically the clock pulse is being taken from this B flip-flop. So this is asynchronous. That means what? This is a combination of synchronous and asynchronous counter. So up till this point, it is your synchronous counter. And from here to here, this is what? This is your asynchronous counter. Okay. So now first, whenever there is synchronous counter, first calculate the counting sequence of the synchronous counter. Okay. Counting sequence. So I haven't told here. So let us take the outputs as QA, QB. So this will be your output. Okay. We are taking output from QA, QB. So, okay. One more thing I haven't told you. So QA is MSB, QB is LSB over here. Okay. So now if that is the case, so let us write the next state equation of A flip-flop. So QA plus will be equal to JA dot QA complement plus KA complement QA, and QB plus is equal to JB QB complement plus. So first see the concept over here, later on you can note. So KB complement QB. Okay. So what can you see? JA is equal to QB. So this is equal to QB, QA complement, and K is equal to 1. So this will be 0. I am not writing. And QB is equal to what? QB plus. It is equal to JB. So JB is equal to, this is QA complement, and this is your QB complement, and KB is 1. So I am not writing it. So now let us see the counting states over here. So if you want to calculate the counting state, so let me write it like this: clock pulse, and over here this is QA QB. I told you what, that QA is MSB because this is synchronous. In synchronous we need to be told specifically which of the flip flop is MSB, which of the flip flop is LSB. So I told you QA is MSB, QB is LSB. So at clock pulse 0, I am initially assuming that the flip flop is reset. So that means 0 0. At the first clock pulse, you can see QA plus is QB complement QA. So that will be 0 and this will be 1. At the second clock pulse, if you see, so QB is 1, QA, so this will be 1, this will be 0. At third clock pulse, so QB 0 means this is 0 and this will be 0. So you are again returning back to the same state. So the state diagram, it will be 0 0, then to 0 1, then to 1 0, and then again back to 0 0. Okay, then again back to 0 0. If suppose we have started from 1 1, is this counter self starting? So let us check that also. If we had started from 1 1, if suppose we had started from 1 1, so then you can see QB dot QA, this will be equal to, the next state will be equal to 0, and over here this will be also 0. Yes, so this is self starting. Even if we start from 1 1, we are going to go to 0 0. So this is not required. Still I told you that this will be a self starting counter. Okay, so very quickly draw. So I am erasing this because this is not required. So very quickly draw the diagram and write it up to this point. Then I am going to tell the next part. Piyush, you have some doubt? You can ask. Fine. So copy it down very quickly. Copy. And Bhumika, you can understand this concept. So this has no relation with whatever I have explained till the last 1 hour. Okay. So basically we are trying to find out the count sequence when we have a synchronous counter and asynchronous counter. Okay. So copied. So till the time you copy, I will just zoom this out a little bit because I want to make something else also. One, two, three, four. Okay, I guess you might have copied it. Oh, I guess this will not fit in the page. Fine, it's okay. So look over here. These are the clock pulses that we have, external clock. Okay, just give me a second. Just give me a second. Okay, so you can see what? Basically, these are negative edge triggered flip flop. So that is why I am taking all the negative edges. So it's actually not strong. It's my elder sister. Okay, so she's talking. I thought means I don't know. Whenever means I actually teach. So my room is just on this means on the front side of our house. So I can hear everyone when they are talking. So that is why I thought means there is a strong outside. So you can see if you look at the state diagram, first state is 0, 0, 0, then you have 0, 1, then you have 1, 0. So first 0, 0. So QA and QB, both of them are 0, 0. So this is QA 0, QB 0. So this is QA, this is QB. Both of them are 0, 0. So the next state at the next clock pulse, it is transitioning to 0, 1. So this will still stay, this will stay at what we saw, QA 0, QB 1. Okay. QA 0, QB will go to 1. In the next state, it is what? 1, 0. So this will go to 1. And this will come back to 0. And in the next state, both of them are 0, 0. Okay. It is 0, 0. And this count state, it will go on until and unless this clock is going on. So I need to copy this. So once again, this will be 0, 0. Then we have 0, 1. Then we have 1, 0. And then again we have 0, 0. So this will go on and on. Okay, like this. You can see this is 1, 0, 0, 1. This is 1, 0. This is 0, 0. Once again we have after 0, 0, 0, 1, then 1, 0, then 0, 0. So this state is continuously going on. Now you can see the negative edge of QB is acting as your trigger for the C. So mark the negative edges. So you can see this will be the negative edge. This is one more negative edge. So at all these places, the flip-flop is going to toggle. Why? Because JC and KC, both of the inputs are 1, 1. Okay. So 1, 1. That means toggling will take place. So over here we have this QC. So this will toggle over here. And once again, we will toggle over here. So continuous toggling is taking place like this. Okay. So now let us write the state. So this is 0, this is 0, this is 1, 1, 1, this is 0, 0. Okay, fine. So now you can see basically this state is what? So if we take, see now for such kind of circuit, okay, for such kind of flip flop, you will be given which is MSB, which is LSB. Okay, you will be given which is MSB, which is LSB. So now if suppose we are taking QC, or you can even see over here, QC is transitioning the less. Okay, QC you can see over here, out of QB and QA, it is toggling the least. So that is why QC will be MSB, and out of QA QB, I have already told you QA is what? It is your MSB and QB is LSB. So sir, please repeat QC part. QC you can see what? This QC is acting as your toggle flip-flop, and the clock is basically QB. Okay, and the negative edges of QB will actually toggle the states. So I have assumed QC is initially 0. So at all the negative edges of QB, it will toggle. So initially if this was 0, here I first encountered what? I encountered a negative edge. Then once again I encountered a negative edge over here. So I have drawn the diagram. So now you can see basically that, okay, first let me tell you, how did I know that in this much state only I will get a repeated state? Because I am a teacher, that is why I know that within 6 clock pulse. So that is why I was counting. So this is 0, 1, 2, 3, 4, 5, 6. Means in total we have 7 clock pulses. So actually I knew beforehand only that within 7 clock pulses I will have a repeated state. So now if you write QC, QA, QB, so this is equal to what? This is equal to 0. So 0, 0, 1. So this is 1. 1, 1, 0. So this is 6. Next is 1, 0, 0. So that is 4. So next will be 1, 0, 1. So this is 5. This is 0, 1, 0. So this is 2. And once again you are getting 0. So now the state diagram for this whole flip-flop, it is what? From 0 to 1, from 1 to 6, from 6 to 4, from 4 to 5, from 5 to 2, and then again back to 0. So now how did I know actually that within 7 clock pulse I will be getting a repeated state? Or basically you can see what is the mod of this flip-flop? Mod. So Raju, did you understand the QC part? Raju, did you understand the QC part? Okay, so what is the mod of this flip-flop? Mod. How many unique states are over here? How many unique states are over here? 6. So obviously this is mod 6 counter. Okay, mod 6 counter. Fine. So now if you see over here, how did I actually know that there will be only 6 states? So that is why I had drawn 7 clock pulses. So look over here. So when I had drawn this, I calculated over here that this is what you can see basically over here. This is mod 3 synchronous counter. So this is mod 3. Okay, this is mod 3. And this is one asynchronous counter, and in asynchronous counter the count sequence we have, it is directly proportional to the number of flip-flop. So here as I have only a single flip-flop, so this will be mod 2. Okay, this is mod 2. So mod 3 into mod 2, it will produce mod 6. So that is why I actually knew that I had to draw 7 clock pulses over here to show you for getting the repeated state. So this is basically what this complete is mod 3. This is mod 2. So in total it is mod 6. So whenever you have a mixture of synchronous and asynchronous counter, you just count the mod number for the synchronous and for the asynchronous and multiply them. You will have the resultant mod of the mixed counter. Is this clear? Tell me. Is this clear? Is this clear? Is this clear? Tell me yes or no. Now one more very important concept I am going to discuss now. happens, so you can see this is the counter. Okay, this is the counting states. What are the unused state here? Because we have 3 flip-flop. So 3 flip-flop can count from 0, 0, 0 to 1, 1, 1. That is from 0 to 7. So over here, you can see that 3 and 7 are not present. 3 corresponds to 0, 1, 1 and 7 corresponds to what? It corresponds to 1, 1, 1. So what happens if I start the flip-flop from, if suppose my this mixed flip means this mixed counter, mixed means what? Synchronous and asynchronous. If it starts from either of these two state, what will be the next count if you want to know? So for that, very quickly, what you are going to do, draw the clock pulses. Okay, draw clock pulse. So don't copy at the moment. First understand, then you can copy, because I will give you the task for calculating the next state when your flip-flop starts from 7. So these are your clock, external clock. Okay. So this is your external clock, this clock. So now when this clock we have, you can see this is what basically the flip-flop are negative edges. So mark the negative edges over here. So this is the negative edge, negative edge, negative edge. And our counting sequence is what? QC, QA, QB. So very quickly draw QA, QB. So we have seen basically when we were at 1, 1. Okay. You can see over here. When we were at 1, 1, we were to the next state 0, 0. I had calculated over here, if you remember. Okay, I had written over here that it was unnecessary and I erased it, but now it will be very necessary when we are at unused state. So now see what happens over here. So when we are at 3, so that means what will be the counting state? It will be 0, 1, 1. So QA, QB is at 1 and 1. So this is 1, this is also 1, this is QA and this is QB, and from 1, 1 we go to 0. Okay, we go to 0, and over here once again we go to 0. Now I am not in the further state, because after 0 you will be going into the count state, 0, 0, 0, 1, 1, 0, again back to 0, 0. You will never return to 1, 1. So it's okay. Up to this point, it is fine. Or even you can draw one more state that after 0, 0, you will go to 0, 1. So this will remain at 0 and this will go to 1. So it's okay. You can even draw this. Now look, basically this QC is what? This QC is acting as it is acting in your toggle mode, and the negative edge of the QB, it will act as your trigger. So where is the negative edge of QB? It is present over here. So basically, if I assume that this flip-flop is initially reset, it is in 0. So what will happen? And you can see over here also that QC is initially 0. So if I start it from 0, so let me take this color. So if I start from 0, in the next state, as there is a negative edge of QB, it will toggle. So it is toggled. Okay. And here this is positive edge. So this will continue to stay at 1. Okay. This will continue to stay at 1. So now you can see this is what? This is your QC. So our basic initial state was from 0, 1, 1. So this is 3. What is the next state? So you can see this is 0, 0. This is 1. This is 0, 1, 0. And our counting state is QC, QA, QB. So QC, QA, QB. So this is 3. This goes where? So QC, QA, QB. So that is 4. And this is 3. So you can see when we start from 4, okay, sorry, when we start from 3, we go to 4. And then once again, sorry, this is not 3. QC, QA, QB. So this is 1. Okay, we are going to 4. After 4, if you check over here, we were going to 5. Have I done some mistake or what? Sorry, what I have written. So this is 1, huh? That is what I was thinking. So this is 5. So you can see we are going into the count state, that is from 3 to 4, then to 5, then from 5 to 2, again to 0. So if we start from a new state 3, we are going to 4. Did you understand this concept, that how we actually knew that when we are at 3 we are going to 4? So this 3 is a new state. Tell me yes or no. Everyone, did you understand? So now I want all of you to draw for 7. From 7, where are we going to go? So very quickly you need to draw. If we start from 7, so 7 means what? QC, QB, QA, QB. So initially my states are 1, 1, 1. So initially this will be what? QA will be 1, QB will be 1. Okay. So this is QA, this is QB. You can see from 1, 1, again back over here. When QA, QB is 1, 1, we go to 0, 0. So this we will come to 0. This will be also 0. Again from 0, 0, we go from 0, 0 to 0, 1. So this will be still 0 and this will be 1. Now look, basically once again the negative edges of QB will act as your trigger for the C flip-flop. So initial state of QC over here is 1. So if we start from 1, we will toggle to 0 and we will stay in the 0 only because there is no more negative edges. So you can see, so this is 1, 1, 1, this is 0, 0, 0, and once again this is 0, 1, 0. So this is 7 and QC, QA, QB. So this is QC, QA, QB. So this is 0 and QC, QA, QB. So this is 1. So you can see from 0 to 1 once again we are coming. So if we start from 7, we are going to 0. Tell if this is clear or not. Yes, Raju, very good. 7 to 0, then to 1. Then we will get the count states. Is this clear? Is this clear? Tell me. Everyone, tell me if this is clear. So such kind of question you will see in your gate paper. Okay, you will see in your gate paper, it will be asked to you guys. Fine. So now let us see over here. So now you can see at this place, this is basically what? This is your, means you can even write, this is your synchronous counter and this much. Okay, so sorry, this is asynchronous and this is synchronous because here the clock is same. Okay, this is asynchronous, this is synchronous. Now how did I know this is asynchronous here? Because I am giving the external clock pulses and the clock pulse for this one is acting as your trigger. Okay, means QC is acting as your clock pulse for JA and JB, means A flip-flop and B flip-flop. So very quickly, I want you to tell me what will be the mod number over here. So quickly tell me what will be the mod. What will be the mod over here? Okay, so you can see this is the external clock, and basically this JC or QC is acting as what? It is acting as your toggle flip flop, because both the input JC and KC is 1 1. So at each of the negative clock edge, the states are going to toggle. So I am assuming initially QC is 0. So if we start from 0, basically it is going to toggle at each of the negative edges of the clock. Okay, so it will look something like this. So now this is very, very conceptual. What will happen over here? Okay, look very carefully. So basically QC is acting as your clock pulses. You can note it down later. Okay, first look over here. So basically the negative edges of QC is acting as your trigger for A flip flop and B flip flop. So mark the negative edges. So this is all the negative edges that we have. Only your flip flop A and B are allowed to change state at this negative edges. Okay. So now this is synchronous counter, and we cannot determine the states of the synchronous counter without the next state equation. So you can see one thing, that I have actually copied this synchronous counter only. Okay. So over here the states are also going to be remaining the same. So clock pulse, basically it is the same. So next state equation is not going to change, and this will be QA, QB. So if I start from 0 0, next state is going to be 0 1. Second state was 1 0, I guess. 0 0 0 1 1 0, and then third will be 0 0. So if you draw the state diagram, it will be also the same. Tell me, up to this point, have you understood? So this is QC. Is this clear? Is this clear? So at the moment, I haven't made any comment about what will be the order. Will it be QA, QB, QC, or will it be QC, QB, QA? So in the question, don't worry, this will be given to you in what order you have to calculate. So don't worry about this. And if it is not given, the state that is toggling the least, it will be MSB, and the state that is toggling the most, it will be your LSB. Okay, so don't worry. So now up to this point, is it clear? So initially I am assuming that QA is what? It is 0 0. QA, QB, both of them are 0 0 at clock pulse 0. So if QA, QB is 0 0, so over here, let us assume that over here I am going to write QA, over here I am going to write QB. So QA is 0, QB is 0. So look, this flip flop, this 2 flip flop, it will change to 0 1 when there is a negative edge of QC. So the negative edge of QC over here, so this will change to 0 1. This is still 0, and you can see at this edge, basically this will change to 1, and this will continue so till the next negative edge. At the next negative edge, the states are going to change from 0 1 to 1 0. So over here this will go to 1, and this will state the change from 1 to 0. And again at the next negative edge of QC, from 1 0, it will go to 0 0. Okay. So you can see 0 0. Once again at the next negative edge, it will go from 0 0 to 0 1. So this will stay at 0. This will go to 1. Okay. So now let us write over here what are the counts we have. So 1 0 1 0 1 0 1. Over here we have 0 0 0 0 1 1 0 0 0. Over here 0 0 1 1 0 0 0 0 1. So out of QA QB, any one of the following can be MSB because both of them are toggling equally. So I am taking what? QA, QB and QC because QC is toggling the most. So you can see this is 0. Okay. So this is 0 0 1. So this will be 1. This is 0 0. Sorry. 0 1 0. So this will be 2. 0 1 1. So this is 3. 1 0 0 4. So 1 0 1. This is 5. Again you are getting 0. And again your counting states will continue. This will be 1. This will be 2. Like this it will go on and on. What is the counting states over here? From 0 to 1, 1 to 2, from 2 to 3, from 3 to 4, from 4 to 5, and again from 5 to 0. So once again you can see this is mod 6 counter. Why? Because the same concept is being continued over here also. This is mod 2. And if you calculate the counting states for the synchronous, it will come out to be mod 3. In total, this will be basically what? This will be mod 6. Okay, this will be mod 6. Now I am leaving homework for you guys. You have to calculate for 6 and 7 that if you start from 6 and 7, what will be your next counting states? Okay, like we have done over here for 3 and for 7, like that only you have to calculate for 6 and 7. Tell me if this is clear or not. If this concept is clear to you guys or not. Is this clear? So note it down very quickly. Then we will move on to our next topic, that is your registers. Okay, so we have to see few register. So today I will just tell you the concept of the registers, and then in the next session we are going to see the questions also. Okay, so very quickly note this down. So look over here. Register. What do we mean by registers? So basically register is what? It is a collection of flip-flop. Okay, it is a collection of flip-flop which we use for storing multiple bits. Okay, it is used for storing multiple bits, that is known as your register. Okay, so if in a register there are different kinds of register. So if in a register the bit shift from one flip-flop to another in a particular direction, either from left to right or right to left, it is known as your shift register. Why? Because the bit positions are basically shifting. So that is why it is known as shift register. Now shift register are basically of 4 type. First is SISO. So serial input, serial output. That means what? The bits are serially going inside the register and it is coming out serially outside the register one by one. Okay, at each, listen very carefully, at each one clock pulse, one bit is entering inside the register, and at the same clock pulse one bit will be coming outside the register. So that is serial input, serial output. Next is SIPO. So that is serial input, parallel output. So that means what? If suppose we have a 4-bit input. Okay, if we have a 4-bit input, so for entering this complete input inside the register, I will require 4 clock pulses. Why? Because serial input, I have told you, at each clock pulse, one of the bit is entering in the register. So serial input, and at a single clock pulse, now I don't know which of the clock pulse, at a single clock pulse, the entire bit is going to come out of the register. So this is serial in, parallel out. Okay, what I said, serial in, parallel out. Next is piezo. So this is parallel input, serial out. So this is not there in our syllabus. Okay, parallel input means what? At a single clock pulse, your input is entering the register, and one by one clock, your output is coming out of the register. Okay, last is what? Parallel input, parallel output. Even this is not there in our syllabus. So nowadays we only use this kind of register, parallel input, parallel output. Why? Because this is the fastest. Okay, this is the fastest. So we have parallel input, parallel output registers, but irony is that we are not going to study piezo or pepo. We are only going to study CISO and CPO. Okay, so serial input, serial output, serial input, parallel output. So let us study one by one. What is CPO? What is this CPO and CISO? Okay, so first is what? We have serial input, serial output. So what I told you, in serial input, serial output shift register, the data input, it will get inside of the shift register bit by bit, or at each clock pulse, one of the bit is going to enter in your register. Okay, so here I am going to show you basically what is CPO, CISO and CPO. So let us assume, last I had assumed this bit. So if this is our data bit, okay, this is our data bit. So you can see what? This is your asynchronous, means I will not say counter. This is your synchronous. This is your what? This is your synchronous flip-flop. This is not counter, okay? This is your register. So you can see what? That basically this is what? Your synchronous register. So if over here I want to write the next state equation, why? Because this is your synchronous, that is why I'm going to write the next state equation. So Q3 plus is equal to D3. So if I write, this is D in, and so let me write it clearly. This is D in, which is equal to 1101. So Q3 plus is equal to D3, that is equal to D in, because we know what? The next state equation of D flip-flop, it is equal to D. Q2 plus will be equal to what? It is equal to D2, and that is equal to Q3. Q1 plus is equal to D1, so D1 is equal to Q2, and Q naught plus is equal to D naught, which is equal to Q1. So this is our next state equation. Okay, so very good. I have actually drawn this thing. So now look over here, that basically this bit is going to enter from from right to left. That means this bit, this one, it is going to enter the flip-flop D3 first, then this 0, then this 1, and then this 1. So now let us see one by one basically how your data is entering the flip-flop. So these are all negative edge triggered flip-flop. So initially the states of flip-flop are 0, 0, 0. So this is your clock pulse 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now look very, very carefully. First, I am going to draw D3. Okay. So D3. So at the first clock pulse, all the flip-flop are basically what? It is 0. So this is D3 is 0. D3 0. D2 0. D1 0. And even D0 0. So it will be better if I write clock pulse, so then it will be easier for you guys to understand and it will be easier for me also to draw. So this is Q3, Q2, Q1, Q0. So initially at clock pulse 0, I am telling everything is 0. Now Q3 is equal to D in. The first bit of D in is 1. So at first clock pulse, D3 is 1. Remaining you can see D2 is equal to Q3. So the initial state of Q3, it was what? The present state, it was 0, 0, 0. That means this 0 is being shifted over here. This 0 is shifted over here. And this 0 is shifted over here. Okay. So I will draw it a little bit properly. Okay. So now look, in the second clock pulse, what will happen? In the second clock pulse, basically, the next bit is going to enter. So why? Because D in, so the next bit is 0. And this one, it is going to shift over here. This 0 is going to shift over here. And this 0 is going to shift over here. Okay. Okay. So now look, we have actually entered these two bits. This 1 is also entered. This 0 is also entered. Now look, in the third clock pulse. So up to this point, are you guys understanding? Let me know. If there is any doubt, you can ask me. Any doubt? Bhumika, Chandana, Piyush, Raju. Any doubt? Anyone? Any doubt? Okay. So now see, the next data, that is 1, it will be entering. So this is 1. This 0 will come over here. This 0 will, sorry, this 1 will come over here. And this 0 will shift over here. Okay. So now look, I should have drawn the diagram a little bit bigger, but it's okay. So now I am not going to draw this arrow, okay, because it will take a lot of time. So now look at the fourth clock pulse, what is happening? This Q out is basically the output of the register. This is the output. See, till this third clock pulse, none of the bit has reached your output. Okay. So now see, at fourth clock pulse, what will happen? The last bit is going to enter D3. So now this will be 1. This bit will shift over here. This bit will shift over here. This bit is going to shift over here. So at fourth clock pulse, you can see the complete input has been loaded in all the flip-flop. Now see what happens in your fifth clock pulse. So this is your output. See, one thing I will tell you, for CISO, only this input side and output side is available. So for CISO, only this input, this output is available. All these intermediate outputs are not available for CISO. Okay. So now look what happens in your fifth clock pulse. So now I will be drawing a little bit quickly. So at fifth clock pulse, you can see what? This input is now over. So what will happen now over here? At Q3, what will be D in? So I can assume this input to be something like this. 1, 0, 1, 1, and then 0, 0, like this, on and on it is going. So because we don't know, so I am going to assume 0. So this will be 0. This one is going to shift over here. This one going to shift over here. This 0 will be coming out here. And this one has come out of the output. This one. Okay. It has come out of the output. Now at 6th clock pulse, one more 0 is going to enter. This 0 will come over here. This 1 will come over here. This 1 will come over here. So you can see In the next case, what is going out? This 0 is going out. Okay, this 0 is going out. So in the next case, in the 7th clock pulse, what is happening? One more 0 is entering and this one is going to shift over here. So this one is going out. In the last case, 8th clock pulse, this is 0, 0, 0 and even this 0 is coming. So this one is also going out. So here you can see first in, last out. Okay, first in, last out is going on. So this was first in, first out. Yeah, so this is first in, first out. Okay, first in, first out. So the first bit that was entering, it is coming out first. Okay, and the bit that was entering the last, it is coming out last. Okay, so here I have taken what? First in, first out. So I guess, wait a minute, I guess I have done some mistake or what? Means I have assumed the data bit is entering. Oh, it's what I did. I took the concept of stack. Sorry, I told you guys the data bit is entering from this bit. I'm very, very sorry. Data bit is entering from left to right. So that is what I was thinking. Why is the sequence of the bit changed over here? So whatever concept we have studied, everything I need to rewrite once again. I'm very sorry. So the bit, it will be entering like this. From this side it will enter. So the first bit that will enter is 1. So at first clock pulse, this one is going to enter. I am very sorry. I have actually taken the concept of stack over here. This is not stack, this is shift register. So the first bit, because we have to preserve the input when it comes out of output. Okay, the data, it cannot be reversed. So I am very sorry. So this one, all the remaining bit is going to be 0. The concept is the same. Okay, just the thing is that I have entered this bit first, then this bit, then this bit, then this bit. Okay, so that is wrong. The first bit should be this bit. So in the second clock pulse, this one will come over here and the next bit is going to enter. So I'm very quickly now doing. So at the third clock pulse, this will be 1, sorry. So 0 will be entering. And this 1 1 0. At the fourth clock pulse, you can see this will be 1 0 1 1. At fifth clock pulse, so this will be 0 1 0 1. This one has actually come out of here. Okay, this one. At sixth clock pulse, this will be 0 0 1 0. So this one is now out. So I will not be drawing over here. Okay, because I want to show you something else also. So at 7th clock pulse, one more 0 will be entering and this will be 1. So this is now over here 0. And in the last clock pulse, that is your 8th clock pulse, this will become completely once again 0 and this one will be also popped out of the register. So this will become 0. So you can see basically the data bit that was entering in the same order, your output also we are getting. Now I told you in CISO, only thing accessible to us is your input terminal and your output. Okay, so you can see basically it took us how many clock pulses to get the first bit. It took us at this particular point, you can see at this, not even this particular point, at this particular 5th clock pulse, we were getting the first output bit. So let me zoom out a little bit. Is this visible to you guys? Because it is very difficult to continuously juggle. So you can see at this 5th clock pulse, basically I am pushing this one out. Okay, so at the 5th clock pulse, I am pushing this one out. Then at the next clock pulse 6, this one is coming out. At 7, this is coming out, and at 8, this is coming out. So this is basically what, look over here. at 6th, 7th, sorry, this is your 5th, 6th, 7th, 8th. At this clock pulses, I am getting the output for CISO. Okay, for CISO, I am getting the output. Now for CIPO, okay, for CIPO, CIPO means what? Serial input, parallel output. All the intermediate outputs are also available to us. Look over here at the 4th clock pulse. At the 4th clock pulse, if I take the output, you are going to see that I will be getting 1101. Wait a minute. 1101. Yes, I will be getting 1101 at the 4th clock pulse. It will be basically what? Q0, Q1, Q2, Q3. Okay. So Q0 is your MSB and Q3 is your LSB. So you can see you are getting the entire data output in a single clock pulse, whereas you have entered the input one by one. See, at first clock pulse you are entering this one, then at second clock pulse the next one, then at third clock pulse this 0 is entering, then at fourth clock pulse this last one is entering, and at the last clock pulse you are actually, means at the 4th clock pulse you are taking out the complete data. So that will be 1101. So this is what? This is your serial input, parallel output. So in serial input, parallel output, the output is coming out at 4th clock pulse. Have you understood the difference between CISO and CIPO? Tell me, is this clear? Is this clear, everyone? Any doubts, anyone? So you can even draw this. Okay, you can even draw this. It is very simple. One by one, if you draw, so this will be very simple. So in the first clock pulse, okay, so where is it? In the first clock pulse, Q3 is 1, all other is 0. So if we assume that this is Q3, this is Q2, this is Q1, this is 0. So at the first clock pulse, Q3 is 1. Remaining all are 0. Okay. In the second clock pulse, Q3, Q2 both 1. So this will stay at 1. Q2 will jump to 1. And the remaining are 0. Okay. So you can complete the diagram on your own. Okay. You can complete the diagram on your own using this table. Tell me if this is clear to you guys or not. Is this clear, everyone? Is this clear? Tell me yes or no. Then only I will understand. Okay. So you can complete this diagram. So next we have is ring counter and Johnson counter. So that is okay. So I will leave you guys over here. So this week we have class. So today we actually did the class of yesterday, that is of Sunday. So tomorrow we have class Tuesday from 8:30. Then we have class on Sunday. Okay. Sunday, are you guys comfortable from 12:30 p.m.? Are you guys comfortable 12:30 p.m.? Is that okay? So once and for all you can actually study, then you guys don't need to come in the evening. Okay, you can enjoy your evening. So that is why I have kept the class on Sunday from 12:30 to 2:30. Okay, so Tuesday also we are going to have class, or you can do one thing, instead of Sunday we can keep the class on Friday also. But Friday I guess I have one function, one occasion I have on Friday, so I cannot be there. So this Sunday kindly adjust on 12:30. Is this okay? So next class is tomorrow at 8:30, and then we have class on Sunday from 12:30. Is that okay?